Lie down now. Let your body sink into your bed. Close your eyes and feel the quiet around you. Take a deep breath and imagine the vast space beyond our small world. The sun hangs in the sky, a glowing sphere of light, calm yet powerful. It seems distant, almost untouchable, but every moment it sends energy that touches every living thing on Earth. Don't miss a night of fresh documentaries. Hit subscribe and share your location in the comments. What's the time in your corner of the world? All right, one more quick question before we begin. Have you ever wondered what would happen if the sun suddenly unleashed its full force directly toward us? The sun is not constant. Its surface roils with motion, a mixture of gases, plasma, and magnetic fields that rise and twist. Every 11 years or so, the sun passes through cycles of activity. Sunspots appear as dark patches on its surface, cooler than the surrounding areas, but markers of intense magnetic fields. These magnetic fields store energy, sometimes releasing it in sudden bursts of light and particles. Solar flares are brief, bright eruptions on the sun's surface. They release radiation across the spectrum, from visible light to X-rays and ultraviolet. When these flares are accompanied by massive ejections of charged particles, called coronal mass ejections or CMEs, they can travel across millions of kilometers to reach Earth. These CMEs are enormous bubbles of magnetized plasma moving faster than 1,000,000 kilometers per hour, carrying billions of tons of solar material. The energy in a large CME can be more than 1 billion hydrogen bombs. The sun's temperament changes over time. Its magnetic fields twist and break, releasing bursts of energy. Sometimes these bursts are small, barely noticeable against the sun's constant glow. At other times, they are extreme, capable of creating effects far from the sun, all the way at Earth. The largest storms recorded, such as the Carrington event in 1859, demonstrate the sun's potential to influence our planet. Scientists can track sunspots and predict periods of high activity, but they cannot foresee every flare or CME. The sun is a star, a living furnace of gas, and like any living system, it has moods, flows, and sudden outbursts. Every second, the sun emits light and particles. Most of the energy arrives steadily, bathing Earth in warmth and light. The solar wind is a constant stream of charged particles flowing outward, moving through the solar system at hundreds of kilometers per second. These particles interact with planets and magnetic fields, shaping atmospheres and sometimes sparking brilliant auroras. During periods of high activity, the solar wind strengthens, and when a CME is launched, this steady stream becomes a powerful gust. Imagine the sun breathing, and suddenly, in one forceful exhale, sending a wave that can reach us in just over a day. Sunspots mark areas where the sun's magnetic field is strong and concentrated. These fields twist and loop above the surface, sometimes breaking and reconnecting. When reconnection happens, energy is released as radiation and plasma. Sunspots often appear in groups, dark against the bright solar disk, and can be larger than Earth itself. Around these spots, the sun may produce flares that radiate light and particles. The more sunspots, the higher the likelihood of intense solar storms. Scientists observe sunspots with instruments that measure light and magnetic fields. The numbers and positions of sunspots help predict the likelihood of future solar events. Coronal mass ejections form above sunspots or in regions of complex magnetic structure. The sun's corona, its outer atmosphere, is extremely hot, millions of degrees Celsius, and filled with charged particles. When magnetic fields in the corona rearrange rapidly, a CME is expelled. The plasma in a CME is hot, dense, and carries a magnetic field that can interact with planets it encounters. The size of a CME can be immense, millions of kilometers across. If it is aimed at Earth, it can compress the magnetosphere and create a geomagnetic storm. The speed and density of the CME determine how strong the impact will be. Solar flares and CMEs are linked, but not always simultaneous. A flare is a burst of light and radiation. A CME is a burst of plasma and magnetic field. Both originate from the Sun's magnetic complexity. The timing, size, and direction are unpredictable. Space weather scientists watch the Sun continuously, using satellites equipped with telescopes that can see in X-rays, ultraviolet, and visible light. Instruments measure the magnetic field of the Sun and detect ejections of particles. Each observation helps us understand the Sun's behavior, though the Sun can still surprise. The energy released by a major solar storm is immense. Even at the distance of Earth, hundreds of millions of kilometers away, the effects can be significant. Solar storms can disturb the magnetic field surrounding our planet, compressing it, shifting currents, and inducing electrical charges in conductors. The interaction is invisible to the eye, but it is powerful. Aurora lights, normally seen at high latitudes, can appear closer to the equator during strong storms. Electrical systems, satellites, and communication networks are all sensitive to these sudden bursts of energy. The Sun's surface is constantly moving. Plasma flows in loops and streams shaped by magnetic fields. When loops twist too tightly, they snap, releasing energy as a flare or CME. These events are natural, part of the Sun's life as a middle-aged star. While the Sun seems calm from Earth, its surface is in constant motion, boiling and twisting. We live in a quiet period compared to other stars, but even so, solar storms remain a real and measurable risk. Understanding this activity helps scientists protect technology and infrastructure on Earth. From the perspective of space, CMEs and solar flares are waves of energy moving outward, invisible yet tangible in their effects. Instruments detect changes in the solar wind, magnetic fields, and particle density. Scientists model how these waves travel, how they interact with Earth's magnetosphere, and what consequences may follow. Each storm teaches more about the Sun, revealing patterns in magnetic field evolution, flare intensity, and particle acceleration. The study of solar storms is ongoing, combining decades of observations with advanced simulations. Even minor solar storms can provide insight. By tracking how the magnetosphere reacts to small CMEs, scientists refine models that predict larger events. Observations of auroras, changes in ionospheric density, and satellite measurements all contribute to understanding. Every storm, large or small, is a piece of data about the Sun-Earth connection. Through this continuous study, we begin to grasp the scale and speed of solar energy and its ability to travel across space, reaching Earth in a matter of hours to days. The Sun's temperament reminds us of the dynamic forces that exist beyond our immediate senses. Though we feel warmth and see light every day, the invisible storms that occasionally erupt demonstrate a powerful connection between our star and our planet. The Sun is a reminder that Earth is not isolated. Even from a distance of 150 million kilometers, the Sun's activity shapes our atmosphere, our technology, and the way life experiences electromagnetic energy. Observing these patterns, scientists prepare for the eventuality of a major solar storm. Each flare, each CME, adds to the quiet but constant story of the Sun's influence. In this first segment, we begin to understand the Sun not as a constant static sphere, but as a dynamic and sometimes unpredictable force. Its cycles, sunspots, flares, and coronal mass ejections are all parts of a system that connects directly to Earth. The Sun is both our source of life and a reminder of nature's vast power, reaching us silently across space. In the coming segments, we will see how these solar outbursts travel, interact with Earth, and affect the technology and systems we rely on every day. Space is not empty. Even though it looks black and silent, it is filled with streams of particles, waves, and magnetic fields. Scientists call these streams space weather. Space weather is the influence of the Sun and its activity on the space around it. It is not weather like rain or wind on Earth, but it can have effects on planets, satellites, and humans traveling in space. Space weather includes solar wind, solar flares, coronal mass ejections, and the radiation that spreads through the solar system. It is a constant presence, shaping the environment far beyond Earth. The solar wind is the main actor in space weather. It is a steady flow of charged particles, mostly protons and electrons, moving outward from the Sun. These particles travel at hundreds of kilometers per second, filling the solar system with plasma. The solar wind is not uniform. Some regions carry faster streams, others slower, and when the Sun erupts with a flare or CME, the solar wind can become a sudden, strong wave of energy. The solar wind interacts with every planet, moon, and asteroid it encounters. It pushes against planetary magnetic fields, creates currents in atmospheres, and sometimes strips away layers of gases from small, unprotected bodies. The entire solar system is surrounded by the Sun's influence, which reaches far beyond the orbit of Pluto. This region is called the heliosphere. The heliosphere is a bubble of charged particles and magnetic field lines extending outward from the Sun. It protects the planets from some of the cosmic rays coming from the rest of the galaxy. The boundary of the heliosphere, called the heliopause, is where the solar wind loses strength and meets the interstellar medium. Inside this bubble, solar activity dominates. Outside, the galaxy's radiation is stronger. The heliosphere is invisible to the eye, but its existence is proven by spacecraft measurements. Probes like Voyager 1 and 2 have traveled beyond the heliopause, confirming the solar wind's reach and the boundary where it fades. Within the heliosphere, space is alive with energy. Magnetic fields twist and tangle, carried by the flow of the solar wind. Particles are trapped along these fields, guided in spirals across millions of kilometers. When a CME is released from the Sun, it rides on the solar wind, moving outward in a vast bubble of plasma. Its front may encounter planets directly in its path, while others experience only the edge of its effects. The journey of a solar storm is long and complex. It travels at different speeds, influenced by the background solar wind, the Sun's magnetic field, and interactions with other charged particles in space. A CME can take less than a day to reach Earth if it is very fast, or several days if it is slower. Throughout this travel, it remains a coherent cloud of energy, with its own magnetic field and plasma density, ready to interact with whatever it meets. Earth, like other planets, has its own magnetic field, which serves as an invisible shield. The magnetosphere is created by the movement of molten iron in the planet's core. It extends tens of thousands of kilometers into space, forming a protective barrier against charged particles from the sun. When the solar wind arrives, the magnetosphere is compressed on the side facing the sun and stretched into a long tail on the opposite side. This shield is dynamic, shifting and vibrating as it responds to the flow of particles. It is not a solid wall, but a fluid boundary that can absorb, redirect, and trap energy. During periods of high solar activity, the magnetosphere experiences stronger currents, shifts its shape, and produces phenomena such as geomagnetic storms and auroras. Charged particles follow the magnetic field lines of the magnetosphere. They spiral around the lines, bouncing between the northern and southern magnetic poles. Some particles are trapped in regions called the Van Allen radiation belts, where they circle Earth for days or even months. Others are deflected entirely, sent past the planet into space. When a CME or a strong solar wind stream reaches Earth, it adds energy to these belts, intensifying the trapped radiation and causing currents to flow through the magnetosphere. The magnetosphere acts as both a shield and a filter, allowing some particles to enter the upper atmosphere while keeping the most dangerous flows away from the surface. Its behavior is observable through satellites, ground-based instruments, and careful measurement of currents and magnetic fields. As particles travel across space, they carry energy and momentum. They interact with other particles and magnetic fields along the way. Collisions are rare, but the collective effect of billions of particles produces measurable forces. Space weather scientists track these particles using instruments on satellites positioned between the Sun and Earth. They measure density, speed, magnetic orientation, and radiation levels. This information allows researchers to predict when a solar storm will arrive and how it might interact with Earth's magnetosphere. The journey from the Sun to Earth is a story of invisible forces moving through a vast and empty space, yet producing effects that can be dramatic when they reach our planet. The solar wind is often steady, but CMEs act as surges or storms. Imagine a calm river, smooth and constant. Now picture a sudden flood, a wall of water moving faster and heavier than the usual flow. That is how a CME travels through space, pushed along by the solar wind and guided by the Sun's magnetic field. As it approaches Earth, the front of the CME may interact with the outer edges of the magnetosphere first, creating a compression and a wave of energy that moves inward. The shape, speed, and magnetic orientation of the CME determine the strength of this interaction. Scientists study these characteristics to understand the potential impact on technology and systems on Earth. The heliosphere not only affects planets, but also the space between them. Asteroids, comets, and interplanetary dust are all embedded in this moving medium. CMEs and solar wind streams can push, deflect, or energize these objects slightly. The Sun's magnetic field, carried outward by the solar wind, interacts with charged particles on these bodies. Even at vast distances, the Sun's activity reaches across the solar system, making space a connected and dynamic environment. This perspective reminds us that our planet is part of a larger system, influenced by forces that move silently across millions of kilometers, invisible yet powerful. Space weather is constantly monitored because of its effects on human technology. Satellites, spacecraft, and astronauts travel through the heliosphere and experience the solar wind directly. Communications, navigation, and Earth observation rely on instruments exposed to these conditions. Sudden solar storms can disrupt signals, damage electronics, or increase radiation exposure. Understanding the heliosphere and the flow of charged particles allows scientists to prepare for these events, to protect equipment and human life. Observations of solar wind and CMEs are combined with models of the magnetosphere to predict how space weather will unfold near Earth. Even in quiet periods, the heliosphere contains streams, waves, and subtle magnetic interactions. Particles from the Sun interact with cosmic rays, producing small but measurable effects. Solar activity is never zero. It is always present in one form or another. By studying this activity over time, scientists can detect patterns and cycles, learning how space weather changes with the Sun's behavior. The heliosphere is a vast laboratory where charged particles move freely, influenced by magnetic forces traveling millions of kilometers to encounter planets like Earth. Each particle carries energy, momentum, and a story of the Sun's recent activity. From the Sun's surface to the edge of the magnetosphere, particles travel silently, unseen, yet shaping the environment of space. The heliosphere acts as a stage, the solar wind as a river, and the magnetosphere as a protective shell. The journey of charged particles is measured in hours and days, but the effects can last longer. Currents are induced in Earth's atmosphere and surface. Satellites experience surges in electricity, and auroras light the skies. Understanding these connections is part of the science of space weather. The study of how solar wind and CMEs move through the heliosphere, how they interact with Earth's magnetic shield, and the effects they produce is ongoing, a careful observation of a system that is vast, dynamic, and invisible. Earth is surrounded by an invisible force, a magnetic field that reaches far into space. This magnetic shield, called the magnetosphere, is created by the movement of molten iron in the planet's core. As the liquid metal moves and flows, it generates electrical currents, which in turn produce magnetic fields. These fields combine into a global magnetism that stretches tens of thousands of kilometers above Earth's surface. From the ground, the magnetic field is invisible, yet it exerts a subtle pull on compass needles, aligns particles in the atmosphere, and shapes the journey of charged particles coming from the Sun. The magnetosphere acts as a protective barrier against the constant stream of solar wind. When charged particles approach Earth, they encounter the magnetic field. Some are deflected around the planet, forced to follow curved paths along magnetic field lines. Others are trapped in regions where the field is strong, spiraling along invisible lines like beads on a string. The structure of the magnetosphere is dynamic. On the side facing the Sun, the field is compressed, squeezed inward by the pressure of the solar wind. On the opposite side, it stretches into a long tail called the magnetotail, which extends hundreds of thousands of kilometers into space. The magnetosphere is not rigid. It moves, bends, vibrates, and sometimes reconnects in response to solar energy. Within this magnetic shield are the Van Allen radiation belts, zones of trapped charged particles. The inner belt lies a few thousand kilometers above Earth, filled mainly with protons. The outer belt is farther out and contains mostly electrons. These belts act as both storage and barrier, holding particles until they lose energy or escape. Spacecraft traveling through the belts require careful shielding to prevent damage from radiation. The belts themselves are invisible, yet their presence is measured by satellites and instruments that record particle energy, density, and movement. They serve as a buffer, slowing down the energetic particles and reducing the intensity of space weather that reaches the planet's surface. The magnetic poles of Earth are key points where field lines converge. Near the poles, charged particles can enter the atmosphere more easily. When a strong solar storm or CME arrives, these particles travel along the magnetic field lines and collide with atoms and molecules in the upper atmosphere. This interaction excites the gases, causing them to emit light. The result is the aurora, visible near polar regions as glowing curtains, ripples, or waves of color in the night sky. Auroras are often green, red, or purple, depending on the type of gas and the altitude of the collision. They are the most visible sign of the magnetosphere at work, a gentle reminder of the invisible forces surrounding Earth. The shape of the magnetosphere changes continuously. Magnetic reconnection occurs when field lines break and reconnect, releasing energy into space and sometimes directing particles toward Earth. These reconnection events are subtle, invisible, yet they can trigger geomagnetic storms that ripple through the magnetosphere. The bow shock forms on the sunward side, where the solar wind slows down abruptly as it meets the magnetic field. Behind Earth, the magnetotail stores energy that can be released later, creating substorms that intensify auroras and currents in space. Observing the magnetosphere requires instruments that can measure magnetic field strength, particle energy, and plasma flows. Each measurement adds to the understanding of this dynamic system. Earth's magnetic field is not uniform. It is slightly tilted relative to the planet's axis of rotation, causing the magnetic poles to drift slowly over time. This drift affects the path of charged particles entering near the poles, slightly shifting where auroras are visible. Magnetic intensity is stronger near the poles and weaker near the equator, which means that particles have a harder time penetrating the shield at low latitudes. The field also has local variations caused by rocks and minerals in the crust, creating subtle disturbances known as magnetic anomalies. These variations can influence the path of particles and the strength of currents induced in the atmosphere and on the ground during geomagnetic storms. Charged particles arriving from the Sun do not strike Earth directly. Instead, they follow the field lines, spiraling and bouncing between the poles. This motion is influenced by the particle's energy, mass, and charge. Lower energy particles tend to be trapped in the Van Allen belts, while higher energy particles can enter the upper atmosphere at high latitudes. During extreme solar events, these streams intensify, increasing the number of particles that reach the atmosphere. As they descend, they create currents in the ionosphere, a layer of charged gas hundreds of kilometers above the surface. These currents can disrupt radio signals, GPS, and other communication systems, but they also produce the soft glow of auroras, a natural light show visible to anyone awake under the night sky. The magnetosphere is a constantly moving system. The solar wind compresses it on the sunward side, stretches it on the night side, and shakes it with waves and oscillations. Magnetic field lines sway, break, and reconnect, transferring energy from space into the Earth's upper atmosphere. These invisible motions are measured by satellites orbiting inside and near the magnetosphere. Instruments record sudden changes in magnetic field strength, particle flux, and plasma density. Scientists use these data to model how the shield responds to solar activity, helping to predict geomagnetic storms before they can affect technology and power systems on Earth. The auroras are not only beautiful, They are informative. Their colors indicate which gases are being excited and at what altitude. Oxygen emits green or red light. Nitrogen emits blue or purple. The patterns show where magnetic field lines are guiding particles, revealing the structure of the invisible shield. During large solar storms, auroras can appear much farther from the poles, sometimes seen near the equator. These displays are not random. They reflect the interaction between energetic particles and the magnetosphere, a visible trace of invisible forces moving silently around Earth. Earth's magnetosphere also protects astronauts and spacecraft in orbit. Satellites passing through the Van Allen belts or near the poles are exposed to higher levels of radiation, which can damage electronics and instruments. Engineers designed spacecraft with shielding and orbit strategies to minimize exposure. Astronauts on the International Space Station receive small doses of radiation from space weather, which vary depending on solar activity. Understanding the magnetosphere allows for careful planning and mitigation, keeping human and technological systems safe even during periods of increased solar activity. Even at the surface, the magnetosphere has effects, though subtle. Magnetic storms can induce currents in long conductors such as pipelines and power lines. These currents are not felt directly by humans, but they can disrupt systems designed to carry electricity. Ground-based instruments detect variations in magnetic field strength during solar storms, providing real-time data for scientists and engineers. These measurements offer insight into how the invisible shield interacts with solar particles and how its dynamic behavior protects the planet while sometimes allowing energy to reach the surface. The magnetic field lines that loop from pole to pole are pathways for particles, guiding them, bending them, and sometimes trapping them. The shape of these lines is determined by the balance of forces between the solar wind and Earth's magnetic pressure. During geomagnetic storms, the field lines are compressed, stretched, and twisted, transferring energy into the upper atmosphere. Subtle vibrations in the magnetic field, called Alphen waves, travel along these lines, moving energy over vast distances in space. This flow is invisible, yet measurable, and it represents the constant dance between the Sun's output and the Earth's protection. The magnetosphere, the Van Allen belts, the auroras, and the magnetic poles together create a system that quietly protects Earth. It is an invisible force, yet it has real effects on technology, space travel, and natural phenomena. Its dynamic nature reminds us that the planet is not isolated, but part of a larger environment shaped by the Sun and the heliosphere. Each particle, each magnetic field line, each flow of current is part of a story that moves silently above and around us. Observing and understanding these forces is crucial for predicting space weather, protecting technology, and appreciating the delicate balance that allows life to exist on a planet shielded from the harsh energy of the Sun. When the Sun releases a coronal mass ejection, it begins a long journey across space. The CME, a massive bubble of charged particles and magnetic fields, moves outward at speeds that can range from hundreds to more than 2,000 kilometers per second. Depending on its speed, it can reach Earth in less than a day if it is extremely fast, or take several days if moving more slowly. During this travel, the CME interacts with the solar wind, the stream of charged particles already flowing from the Sun. It can be pushed, slowed, or deflected slightly by the background wind, but it generally maintains its shape and coherence as it moves toward the planet. The size of a CME is immense, often millions of kilometers across. Its outer edges may brush past Earth, even if the main body is not directly aligned with the planet. Scientists track CMEs using satellites equipped with cameras and instruments that measure light and magnetic fields. These observations allow predictions of the arrival time and intensity of the event. A fast CME carries a strong magnetic field and a dense cloud of particles capable of producing significant geomagnetic effects. Slower CMEs, or those less dense, may have only minor effects, barely noticeable against the natural variations of space weather. Solar storms vary in intensity. Minor storms produce small fluctuations in the magnetosphere, sometimes detectable only by sensitive instruments. Moderate storms can cause visible auroras at lower latitudes than usual and may induce currents in power lines or pipelines. Extreme storms, rare but possible, can compress the magnetosphere dramatically, producing strong geomagnetic currents, disrupting satellites and affecting technology on a large scale. Scientists classify these events using scales that measure the strength of geomagnetic disturbance and the amount of energy carried by the CME. Historical events, such as the Carrington event of 1859, demonstrate the potential severity of extreme storms, where auroras were seen near the equator and telegraph systems experienced disruptions and sparks. As a CME approaches Earth, the first point of contact is the magnetosphere. The front of the cloud pushes against the magnetic field, compressing it on the side facing the Sun. This compression is measurable. The bow shock forms where the solar wind suddenly slows and bends around the magnetosphere. The field lines on the sunward side are pushed closer together, while the magnetotail on the opposite side stretches further into space. This deformation is dynamic, fluctuating as the CME interacts with the magnetic field. Currents are induced within the magnetosphere, transferring energy through its structure. Some of this energy is dissipated in the outer atmosphere, while other portions feed into trapped particles and radiation belts. The interaction of a solar storm with Earth is governed by the orientation of the magnetic field carried by the CME. If the magnetic field of the CME is aligned opposite to Earth's magnetic field, it allows magnetic reconnection to occur. This reconnection releases energy from the solar wind into the magnetosphere, increasing currents and accelerating particles along field lines toward the poles. The result is a geomagnetic storm, an event where the magnetic environment around Earth is disturbed. During such storms, the intensity of auroras increases, ionospheric currents strengthen, and induced currents appear in long conductors on the ground. This is all a natural consequence of electromagnetic forces, occurring without any dramatic noise or visible violence in space. The magnetosphere responds like a flexible, conductive shield. As the CME presses inward, the field lines vibrate and bend. Electrons and protons spiral along these lines, gaining energy from the shifting magnetic environment. The Van Allen belts can swell with newly energized particles, increasing radiation levels. Some particles escape along the magnetotail, entering the night side of Earth's magnetic environment. These movements are continuous and predictable, based on the physics of charged particles and magnetic fields. Satellites monitor the flow, recording magnetic field strength, particle flux, and plasma density as the CME passes. These measurements reveal a delicate but powerful dance of energy between the Sun and the planet. Different regions of the magnetosphere are affected in distinct ways. The day side, facing the Sun, experiences compression as the CME pushes against it. The night side, extended into the magnetotail, stores energy that can be released later through substorms. These substorms accelerate particles into the polar regions, creating intense auroras and injecting currents into the upper atmosphere. Scientists have observed that the shape of the magnetosphere can change in minutes as a CME passes, stretching, twisting and vibrating in response to the incoming energy. The motions are subtle, measurable only with sensitive instruments, yet they represent the transfer of vast amounts of solar energy across millions of kilometers. The speed and density of the CME determine the intensity of the geomagnetic storm. Faster, denser clouds carry more energy and produce stronger interactions. Scientists measure this energy using parameters such as the speed of the cloud, the density of particles, and the orientation of its magnetic field. These measurements allow them to classify the storm, predict aurora activity, and anticipate potential effects on technology. Minor storms may only create visible auroras at high latitudes, while extreme storms can disrupt satellites, communication networks, and power systems, even inducing currents thousands of kilometers away from the polar regions. Solar storms also affect the ionosphere, the upper layer of Earth's atmosphere. When energetic particles enter this region, they collide with atoms and molecules, producing currents and increasing the density of charged particles. These changes can affect radio signals, GPS accuracy, and other forms of communication that rely on the ionosphere to propagate. The effects are measurable and scientifically explained by the physics of charged particle motion, electromagnetic induction, and plasma behavior. Each solar storm provides new data about how energy from the Sun moves through space and interacts with Earth's protective magnetic field. The arrival of a CME is not sudden in the sense of a shock that is visible to the eye. It is a gradual physical process where the cloud of particles moves through space, interacts with the magnetosphere, and redistributes energy. Instruments detect changes in particle density, speed, and magnetic orientation well before the CME reaches the upper atmosphere. This allows scientists to warn satellites, operators of power grids, and astronauts about potential disturbances. The predictability is based on careful observation of solar activity, models of the solar wind, and understanding of magnetic reconnection. It is a precise, measurable sequence of events that begins at the Sun and continues across space. Extreme solar storms can compress the magnetosphere significantly. The bow shock moves closer to Earth, sometimes within tens of thousands of kilometers of the surface. Magnetic field lines are forced inward, currents intensify, and radiation belts are energized. The resulting geomagnetic storm can induce currents in long conductors such as pipelines and power lines, affect satellite electronics, and create auroras visible far from the poles. These physical processes follow well-understood laws of electromagnetism. Each effect is the result of particles interacting with magnetic fields, moving in predictable ways, and transferring energy from space into the near-Earth environment. Solar storms are studied carefully to understand their timeline. From the moment a CME leaves the Sun to its first contact with the magnetosphere, the cloud travels at high speed through the heliosphere. Depending on its initial speed and density, it may reach Earth in a day or several days. Scientists use observations of sunspots, flares, and CMEs to predict arrival times. Satellites measure the incoming solar wind, detect changes in magnetic field orientation, and provide early warning. These measurements allow operators to protect satellites, adjust spacecraft orientation, and warn of potential disruptions to technology and communications. The physical processes occurring during the arrival of a solar storm are complex, but follow the principles of electromagnetism and plasma physics. Particles carry charge and mass, magnetic fields exert force, and energy is transferred through interaction. The magnetosphere compresses, stretches, and reconnects. Currents flow through plasma in space and the upper atmosphere. Energetic particles spiral along field lines, some entering the atmosphere to create auroras. Each stage of the storm can be measured and modeled. There is no drama in the conventional sense, only precise interactions of natural forces across vast distances. By studying multiple events, scientists understand the variability of solar storms. Minor events provide insight into the magnetosphere's normal behavior. Moderate storms reveal how auroras extend to lower latitudes and how currents are induced in long conductors. Extreme storms show the maximum potential of energy transfer from the Sun to Earth. Each CME is unique, with different speed, density, magnetic orientation, and size. The arrival of each storm adds to the growing knowledge of how the Sun and Earth interact. This understanding helps protect technology, maintain communication systems, and ensure the safety of astronauts and aircraft exposed to high altitudes. Even after the CME passes, its effects continue. Energized particles remain in the radiation belts for hours or days. Currents in the ionosphere slowly dissipate. The magnetosphere returns to its normal shape, but not instantly. Substorms may release additional energy stored in the magnetotail. Satellites continue to detect elevated radiation levels. The entire process, from the Sun to Earth, is a flow of energy through space, following the laws of physics. It is a continuous, measurable, and predictable phenomenon that demonstrates the dynamic connection between our planet and its star. When charged particles from the Sun enter Earth's magnetic field, some are guided along field lines toward the polar regions. These particles, mostly electrons and protons, travel at high speed and collide with atoms and molecules in the upper atmosphere. The collisions excite the atoms, causing their electrons to jump to higher energy levels. As the electrons return to their original states, they release energy in the form of light. This process creates auroras, glowing displays in the sky that trace the movement of energetic particles along magnetic field lines. The auroras are a visible connection between the Sun and Earth, a natural signal of invisible forces at work. Auroras appear at high altitudes, typically between 80 and 300 kilometers above the Earth's surface. The exact altitude depends on the type of particle, its energy, and the composition of the atmosphere in that region. Oxygen atoms, for example, emit green light at around 100 kilometers, while red light occurs at higher altitudes above 200 kilometers. Nitrogen molecules can produce blue or purplish-red light, depending on the energy of the collision. Each color represents a specific interaction between charged particles and atmospheric gases. Observers on the ground can see the patterns of light, often as curtains, arcs, or diffuse glows stretching across the sky. The location of auroras is determined by the Earth's magnetic field. They are most common near the magnetic poles, in regions known as the auroral ovals. In the northern hemisphere, they are called the aurora borealis, or northern lights. In the southern hemisphere, they are called the aurora australis, or southern lights. During quiet periods of solar activity, auroras are confined to high latitudes. During stronger solar storms, they expand to lower latitudes, making them visible to populations far from the poles. The movement and shape of auroras can vary quickly, reflecting the changing energy of particles entering the atmosphere and the dynamic configuration of the magnetosphere. The physical chemistry of auroras involves excitation and de-excitation of atmospheric atoms. When high-energy electrons strike oxygen or nitrogen, they transfer energy that pushes electrons in those atoms to higher orbitals. This is a non-destructive process. The atoms remain intact, but the energy must be released. The release occurs as light, and the wavelength of the light depends on the energy levels of the atom and the altitude of the collision. This is why different colors appear at different heights. The light is emitted in all directions, but magnetic field lines guide the motion of particles, giving auroras their characteristic shapes. The energy in auroras is small compared to the total energy of the incoming solar storm, yet the visual display is striking and informative. Auroras are not uniform. They can appear as thin, undulating curtains, wide, diffuse glows, or bright arcs. They may shimmer, pulse, or move slowly across the sky. These patterns result from variations in the density and energy of incoming particles, changes in the magnetic field, and fluctuations in atmospheric composition. Satellites above the auroras can measure the particle flux, plasma density, and electric currents associated with these displays. Ground-based cameras and photometers record changes in brightness and color. Each aurora is unique, reflecting the specific conditions of the magnetosphere and solar wind at that moment. Observing auroras provides a window into the complex interactions of charged particles, magnetic fields, and atmospheric gases. During major geomagnetic storms, auroras can extend to unusual latitudes. In some historical cases, such as the Carrington event of 1859, auroras were reported near the equator. In more recent moderate storms, auroras have been seen as far south as the continental United States and Central Europe. These low-latitude auroras are less intense than those near the poles, but still visible and scientifically significant. Their appearance indicates that the magnetosphere is under stress, allowing particles to penetrate regions normally protected from direct entry. Such events provide valuable data on how the magnetosphere responds to extreme solar energy. The auroras are also influenced by the type of incoming particles. Electrons are primarily responsible for visible light emissions, while protons contribute to other phenomena, including ionization in the upper atmosphere. The proportion of electrons to protons in a solar storm affects the brightness and color composition of the aurora. During strong storms, the auroras can be bright enough to cast shadows at night or illuminate landscapes with a soft glow. The shifting colors and patterns provide a continuous, changing display, a natural consequence of electromagnetic and chemical interactions occurring hundreds of kilometers above the surface. Auroral currents flow along magnetic field lines, forming what are called Birkeland currents. These are streams of charged particles moving between the magnetosphere and the ionosphere. As the particles descend, they collide with atoms in the atmosphere, creating both light and electrical currents. These currents are measurable and influence the Earth's magnetic environment. Instruments detect changes in magnetic field strength on the ground that correspond to auroral activity. The interplay between currents, particles, and light creates a system in which energy from the sun is absorbed, redistributed, and partially radiated as visible illumination. Auroras provide insight into space weather. By observing their shape, movement, and brightness, scientists can infer the strength and orientation of the incoming solar wind and CMEs. During geomagnetic storms, the auroras become a real-time indicator of the magnetosphere's response to solar activity. Satellites in orbit record high-energy particle interactions, while ground-based observers capture the light patterns. Together, these observations form a detailed picture of how energy from the sun moves through space, interacts with the magnetosphere, and affects the atmosphere. The aurora is not merely a visual phenomenon. It is an observable manifestation of electromagnetic physics on a planetary scale. The altitude of auroras also influences how they affect the atmosphere. Collisions at higher altitudes produce red light and contribute to ionization in the upper layers of the thermosphere. Collisions at lower altitudes produce green or blue light and affect the lower ionosphere. The redistribution of charged particles can influence atmospheric conductivity and affect radio wave propagation. During strong storms, the aurora region can expand downward, altering the ionosphere over a wider area. These changes are scientific and measurable, illustrating the direct link between solar activity, particle motion, and atmospheric chemistry. Auroral displays evolve over time. During a storm, auroras may appear first as faint glows at high latitudes, then intensify and move equatorward as the storm strengthens. Patterns may shift rapidly, reflecting changes in the solar wind and the reconnection of magnetic field lines. The speed and direction of particle flow influence how auroras form, creating waves, arcs, and folds in the glowing curtains. These movements can last for hours, gradually diminishing as the solar storm passes and the magnetosphere returns to a more stable state. Observers on Earth experience these changes as a continuous, flowing spectacle of color and motion. Auroras are not only scientifically informative, but also visually immersive. The soft, shifting glow, the delicate arcs, and the curtains of color offer a way to perceive the otherwise invisible interactions occurring above the planet. They are a reminder of the magnetosphere at work, of charged particles traveling across millions of kilometers, and of the sun's energy interacting with Earth's protective shield. While the auroras themselves are beautiful, they are also indicators of electromagnetic processes, particle motion, and energy transfer occurring in a system far larger than any human-made structure. Observing them connects us to the solar system in a direct, sensory way. During extreme geomagnetic storms, auroras can last for many hours, sometimes filling the night sky with continuous light. Satellites measure increased particle density and currents associated with these extended displays. Ground instruments detect prolonged magnetic fluctuations, showing that the magnetosphere remains energized even after the initial solar storm has passed. The auroras gradually fade as the inflow of particles decreases and the magnetosphere stabilizes. This fading is part of a natural cycle, reflecting the dynamic interaction between Earth and the Sun over space and time. In addition to visual effects, auroras influence the atmosphere electrically. The collisions of charged particles with gases create currents and ionization that can alter the conductivity of the ionosphere. These changes can affect radio communication and satellite signal transmission. Scientists monitor auroral activity to understand these effects and to provide warnings for technology that depends on stable atmospheric conditions. The aurora is a physical process with real measurable consequences, linking sunlight and space weather to the environment in which humans operate. Every aurora is unique, a product of the specific conditions of solar wind, CME structure, and magnetospheric configuration at that moment. No two displays are exactly alike. By studying variations in auroral patterns, scientists learn about the strength, direction, and composition of incoming solar particles. These observations feed into models of space weather, helping predict future storms and their effects. The slow, flowing nature of auroras mirrors the gentle, continuous movement of energy from the sun, providing a visual representation of forces that would otherwise remain unseen. Auroras are both delicate and powerful. They glow softly across the sky, yet represent vast amounts of energy flowing through the magnetosphere and into the atmosphere. Each collision of a particle with an atom is a tiny event, but collectively they produce light visible across hundreds or thousands of kilometers. The patterns, colors, and movement all trace the invisible paths of electrons and protons guided by magnetic fields. Observing auroras is a direct way to perceive the physics of space weather, the interaction of the sun and earth, and the flow of energy through the upper atmosphere. Through careful measurement and observation, scientists connect auroras to specific solar events. By tracking changes in particle flux, magnetic orientation, and energy density, researchers can correlate auroral activity with the arrival of CMEs and solar flares. These correlations provide insight into the processes occurring in the magnetosphere, showing how the solar wind is converted into visible light and currents in the atmosphere. The aurora is a window into the complex system of space weather, offering a natural, observable signal of energetic processes that occur far above and beyond our daily environment. Even when seen from thousands of kilometers away, auroras remain a quiet and continuous process. The light moves slowly, responds to shifts in particle flow, and fades gradually as energy is absorbed or redirected. The atmosphere acts as a medium that translates particle motion into light, creating displays that are both informative and beautiful. Auroras are the most immediate and visible effect of solar storms, a direct manifestation of the interaction between charged particles from the sun and the magnetic and atmospheric systems of Earth. They allow humans to sense, without instruments, the presence of invisible forces shaping our planet. The energy carried by solar storms does not remain in space. When charged particles from the sun enter the magnetosphere, they induce currents in the upper atmosphere. These currents, called geomagnetically induced currents, flow through conducting materials on Earth, such as power lines, pipelines, and undersea cables. The strength of these currents depends on the intensity of the solar storm, the orientation of the magnetic field, and the length and conductivity of the structures they flow through. Even subtle changes in the magnetic field can create small but measurable currents, while extreme events can produce flows strong enough to disrupt electrical systems over large regions. Satellites in orbit are directly exposed to solar storms. High-energy particles can penetrate shielding and affect sensitive electronics. When energetic electrons enter satellite circuits, they can cause single-event upsets, a type of error that can disrupt computer memory, processing, or communication systems. Solar storms also produce increased drag on satellites in low Earth orbit. The upper atmosphere heats and expands due to energy deposited by incoming particles, increasing air density at altitudes where satellites travel. This creates additional friction, slightly slowing satellites and altering their orbits. Operators must adjust trajectories and sometimes shut down systems temporarily to prevent damage. Communication systems that rely on radio waves, including high-frequency signals, can be affected by changes in the ionosphere during geomagnetic storms. The influx of charged particles modifies the density and structure of the ionosphere, which bends, absorbs, or reflects radio waves differently than during quiet periods. This can lead to signal fading, distortion, or complete loss over certain frequencies. Aviation and maritime operations that rely on radio communication or GPS signals are particularly sensitive. Satellites transmitting GPS data may experience temporary errors due to disturbances in the ionosphere, causing navigational inaccuracies on the ground or in the air. Power grids are particularly vulnerable to geomagnetic storms. When geomagnetically induced currents flow through long transmission lines, they can enter transformers and other equipment designed for alternating current. Unlike standard power flow, these quasi-direct currents can saturate transformer cores, producing heat and potentially damaging insulation. This damage can lead to outages, reduced capacity, or permanent failure. Utilities monitor geomagnetic activity and can adjust grid operations during strong storms, such as by redistributing loads, temporarily disconnecting vulnerable equipment, or activating protective devices. The vulnerability of electrical systems to space weather is a direct consequence of the interaction between induced currents and the design of human technology. Historical examples provide concrete illustrations of these effects. The Carrington event of 1859 was the most powerful recorded solar storm in modern history. Telegraph systems, the dominant communication network at the time, experienced widespread disruptions. Telegraph operators reported sparks, fires, and messages sent without power due to currents induced in long telegraph lines. Auroras were visible near the equator, far from their usual high-latitude locations. This event demonstrates the potential for extreme solar storms to impact electrical systems, even before the existence of modern power grids and satellites. In more recent history, the Quebec blackout of 1989 provides a case of a geomagnetic storm affecting a modern power grid. A moderate solar storm induced strong currents in the Hydro-Quebec power network. Transformers became saturated, protective systems tripped, and the entire grid collapsed, leaving millions without electricity for hours. The storm's effects were amplified by the specific design and orientation of transmission lines and the local geology, which influenced how currents flowed through the ground. This example shows that even today, electrical infrastructure can be disrupted by solar activity, with predictable and measurable physical processes at work. The chain reaction in electrical systems begins with induced currents. These currents flow through long conductors and into transformers, causing magnetic saturation and heating. Protective devices detect abnormal current levels and may disconnect equipment to prevent damage. Disconnecting one component can shift load to other parts of the grid, increasing stress and potentially tripping additional systems. In extreme cases, this cascade can lead to wide-area outages. Engineers study these processes carefully, modeling how geomagnetically induced currents propagate through networks, and how to mitigate risk. Understanding the physics of both the solar storm and the electrical infrastructure is essential for prevention. Transformers are especially sensitive because they rely on magnetic cores to convert voltage levels efficiently. When exposed to quasi-direct currents induced by geomagnetic storms, the cores experience additional magnetic flux that was not accounted for in the design. This extra flux produces heat, vibration, and sometimes electrical noise. Repeated or extreme exposure can damage the windings or insulation, leading to long-term degradation. Utilities plan for geomagnetic storms by monitoring space weather forecasts, installing protective devices, and designing transformers to tolerate certain levels of induced current. These precautions rely on understanding the detailed physics of energy transfer from space into infrastructure. Pipelines can also experience effects during geomagnetic storms. Currents induced in the ground flow through pipelines, potentially accelerating corrosion. Monitoring systems detect fluctuations in current and voltage along the pipeline, allowing operators to take protective measures. While these effects are less immediately visible than power outages, they illustrate that geomagnetic storms influence a range of human systems. Any long conductor, whether it carries electricity, oil, or water, can be subject to small electrical currents induced by shifting magnetic fields during a solar storm. Satellites in geostationary orbit experience unique challenges. Energetic particles can accumulate charge on surfaces, creating differences in electrical potential. These charges can discharge suddenly, producing small arcs or electrical disturbances that affect onboard systems. Solar panels may experience degradation, reducing power output over time. Instruments measuring magnetic fields or radiation must account for the variable environment created by geomagnetic storms. Satellites are designed to tolerate these conditions, but extreme storms still pose risks, especially for older or unshielded equipment. Solar storms also influence aviation. Flights at high latitudes, particularly near the poles, are exposed to increased radiation levels. During strong geomagnetic storms, pilots and passengers receive higher doses of cosmic and solar radiation. Airlines may reroute flights to avoid the most affected areas, reducing exposure. High-frequency radio communication may be disrupted, requiring backup navigation methods. The physical basis for these effects is well understood. Charged particles penetrate the atmosphere more easily near the poles, guided by Earth's magnetic field, and interact with electronic systems in aircraft and satellites. Modern technology is interconnected, which amplifies the impact of geomagnetic storms. A disruption in satellite communication can affect GPS-dependent systems on the ground, influencing navigation, banking, and logistics. Power outages in one region can cascade to neighboring areas. The interaction between space weather and infrastructure demonstrates that the influence of solar storms is not limited to one system, but can propagate through multiple networks simultaneously. Scientists and engineers study these interactions carefully, using observations from satellites and ground-based instruments to model and mitigate the risks. The predictability of geomagnetic effects has improved with satellite monitoring of solar activity. Instruments detect CMEs, solar flares, and variations in the solar wind. Data are transmitted in near real time, allowing operators of satellites, power grids, and communication networks to prepare. Protective measures may include reorienting satellites, reducing load on transformers or temporarily shutting down vulnerable equipment. These actions reduce the chance of damage and illustrate how understanding the physics of solar storms translates directly into practical defense measures. Even during minor storms, induced currents can subtly influence electrical systems. Sensitive equipment may detect small voltage fluctuations or magnetic disturbances. Engineers use these observations to refine models of how geomagnetic energy flows through networks. By comparing real events with simulations, scientists can predict which components are most at risk during stronger storms. This continuous monitoring and study ensures that electrical systems are resilient and capable of responding to the natural forces that arrive from space. The energy from solar storms, while invisible, follows predictable physical laws. Magnetic fields carry energy, charged particles flow along these fields, and currents are induced in conductive materials. The resulting effects on satellites, communication systems, and power grids are the natural outcome of these interactions. Each component of infrastructure responds according to the physics of electricity and magnetism, and each response can be measured, modeled, and mitigated. The study of these effects allows human technology to coexist safely with the dynamic environment created by the sun. Geomagnetic storms influence a wide range of electrical systems. Satellites may experience electronic errors or orbital changes. Radio and GPS signals can be disrupted, and power grids may face currents that damage transformers. Historical events like the Carrington event and the Quebec blackout provide clear examples of these processes. The underlying mechanisms are physical and predictable. Charged particles, induced currents, magnetic fields, and infrastructure interactions. By understanding these processes, scientists and engineers can protect systems, ensuring continuity of power, communication, and satellite operations even during strong solar activity. Solar storms influence technology in ways that are both subtle and profound. The energy carried by charged particles and magnetic fields from the sun can reach Earth and affect systems that rely on electricity, radio waves, or conductive materials. Aviation is one area where solar storms are particularly relevant. Aircraft flying at high altitudes, especially near the poles, are exposed to increased levels of radiation. This radiation comes from energetic particles guided by the magnetic field into the upper atmosphere. Pilots and passengers at cruising altitudes, where the atmosphere is thinner, receive higher doses of cosmic and solar radiation than they would at ground level. Airlines monitor space weather reports and may adjust flight paths to avoid regions where solar activity is strongest, rerouting polar flights to lower latitudes during severe storms. Radiation exposure during flight is measurable, but generally remains below hazardous limits for occasional travelers. Frequent flyers and crew who fly near the poles more often receive higher cumulative doses. Instruments on aircraft measure cosmic radiation continuously, and space weather agencies provide forecasts to airlines. During extreme solar storms, such as those with strong CMEs, radiation levels can increase substantially. These forecasts allow preventive actions, such as altitude adjustments or temporary rerouting, to maintain safety. The physical processes at work involve particles entering the atmosphere along magnetic field lines, colliding with atoms in the upper layers, and transferring energy that is absorbed by materials and biological tissue. Spacecraft are similarly affected by solar storms. Satellites in orbit are exposed to energetic electrons and protons that can penetrate shielding. When high-energy particles strike electronic components, they can create single-event upsets, temporarily disrupting memory, processors, or communication systems. In more severe cases, sustained exposure can degrade materials, damage solar panels, or reduce the efficiency of power systems. Satellite operators take precautions by adjusting orientation, shutting down sensitive instruments, or switching to backup systems during predicted solar storms. Low Earth orbit satellites are especially sensitive to increased atmospheric drag. When the upper atmosphere heats and expands due to solar energy, satellites experience additional friction, slightly slowing their orbits. Operators must adjust trajectories to maintain proper altitude and prevent orbital decay. Radiation shielding is a critical consideration for satellites and spacecraft. Shielding materials, such as aluminum or specialized composites, can reduce the number of energetic particles reaching sensitive electronics. The thickness and composition of shielding are calculated based on expected solar activity and mission duration. In extreme solar storms, however, even well-shielded satellites can be affected. Operators rely on real-time measurements from monitoring satellites to make decisions about system operation, power allocation, and mission timing. These procedures ensure that the technology continues to function despite the dynamic environment of space. Undersea cables are another part of modern infrastructure influenced by geomagnetic activity. While the ocean provides some protection from direct particle effects, geomagnetically induced currents can travel through long conductive structures that link continents. The cables themselves may carry data signals, while the surrounding conductive environment can allow currents to flow along grounding systems. Operators monitor voltage fluctuations, and protective systems detect abnormal currents to prevent damage. Although these currents are typically small, during intense geomagnetic storms, the effects can propagate along the cable network, creating challenges for the continuity of global communications. Pipelines are affected by similar processes. Currents induced in the ground can flow through long metal pipelines, potentially accelerating corrosion. Monitoring systems along the pipeline detect changes in voltage and current, allowing operators to adjust protective measures. These effects, while slow to cause immediate disruption, demonstrate that geomagnetic storms influence not only the visible or electronic systems, but also infrastructure buried or submerged, showing the broad reach of solar energy once it interacts with the Earth's magnetic field. Modern transport systems rely on satellite navigation, electrical systems, and communication networks, all of which can be influenced by solar storms. GPS signals may become less accurate as ionospheric conditions fluctuate. Navigation errors can propagate into aviation, maritime shipping, and ground transport. Communication networks, both terrestrial and satellite-based, can experience delays, noise, or temporary outages during geomagnetic storms. The effects are well documented and are predictable through the physics of charged particles interacting with Earth's magnetic and conductive environment. Operators of these systems incorporate space weather forecasts into operational planning to reduce risk and maintain safety. The interplay between solar storms and modern technology is observable during periods of strong solar activity. For example, during the Halloween solar storms of 2003, satellites experienced temporary malfunctions, airlines rerouted flights to avoid polar regions, and power grids in some regions experienced minor voltage fluctuations. These events provide real-world data on how interconnected infrastructure responds to energetic particles and induced currents. Scientists analyze satellite telemetry, ground-based measurements, and atmospheric data to understand the physical processes and improve protective strategies. Even everyday electronic systems can be subtly affected. High-frequency communication may experience short-term interference, especially in regions where ionospheric disturbances are strongest. Ground-based radio systems, long-distance telephone lines, and even some unshielded electronic equipment may experience transient effects. These impacts are typically minor but measurable, illustrating that geomagnetic energy propagates through multiple layers of infrastructure. The continuity of services depends on careful monitoring, redundant systems, and understanding the underlying physics that governs energy transfer from space into technological systems. Space weather can affect transport in broader ways as well. Aviation and maritime navigation rely heavily on satellite systems for position, timing, and communication. Solar storms can degrade GPS signals, producing errors in location data that operators must correct. Precise timing for financial networks, energy grids, and transportation coordination also depends on accurate satellite clocks, which can be influenced by geomagnetic activity. Understanding these connections allows operators to anticipate potential disruptions and maintain the integrity of global systems that rely on coordinated timing and navigation. The physical explanation for all these effects lies in the interaction between charged particles and Earth's magnetic field. When a solar storm sends energetic electrons and protons toward the planet, the magnetosphere deflects many of them, while others follow magnetic field lines toward the poles. As particles descend into the atmosphere, they generate currents and ionization. These currents can flow along conductive pathways on the ground or within technological systems. The magnitude and distribution of the currents depend on particle energy, density, the orientation of magnetic fields, and the length of conductors. The resulting effects on technology follow the laws of electromagnetism and material physics, and they are predictable given appropriate measurements and models. Satellites illustrate the chain of influence clearly. Energetic particles cause localized charging or discharges on surfaces. These discharges can upset electronic circuits or trigger protective systems. The effects can cascade, as a disrupted communications satellite may delay signals for aircraft navigation, shipping logistics, or emergency communications. Ground-based power systems may simultaneously experience induced currents, requiring adjustments to maintain stability. Each layer of technology responds to space weather in a measurable way, and the interactions can be mapped, monitored, and mitigated through careful planning. Even infrastructure hidden from view, such as undersea cables and pipelines, participates in this interaction. Induced currents follow the path of least resistance, traveling through metallic structures and connected systems. Monitoring equipment can detect these currents, and operators can take preventative measures, such as adjusting grounding or flow of electricity. These effects may not be immediately noticeable, but they illustrate the broad reach of energy originating from a solar storm, extending from outer space to the depths of the oceans and the layers of the Earth's crust. Technology in space and on the ground is resilient but not invulnerable. Engineers use forecasts, real-time data, and historical knowledge to prepare for solar storms. Redundant systems, shielding, and operational adjustments allow satellites, aircraft, and communication networks to continue functioning. Power grids are designed with protective devices and procedures to mitigate the effects of induced currents. By understanding the physical mechanisms at work, from charged particles to induced currents, humans can maintain safe and reliable operation of technological systems even during periods of heightened solar activity. The continuous interaction between solar storms and human infrastructure demonstrates that no system exists in isolation. Aviation, space travel, communication, and power distribution are all connected by the flow of energy through charged particles, magnetic fields, and conductive materials. Observing the effects of solar storms allows scientists and engineers to refine models, improve prediction, and enhance safety. The real-world examples, such as rerouted flights, satellite adjustments, and grid protections, show how knowledge of space weather translates directly into operational practice, maintaining continuity in a modern, technologically dependent world. Solar storms illustrate the delicate balance between human technology and natural forces. While the effects on aviation, satellites, pipelines, and power systems may seem complex, they are governed by straightforward physical principles. Charged particles follow magnetic field lines, induce currents in conductors, and interact with electronic systems. The scale of these interactions spans thousands of kilometers, from orbital altitudes to ground-based infrastructure, and even beneath the oceans. By observing, measuring, and modeling these processes, scientists provide the foundation for safe operation of transport and technological systems in a space environment influenced by the sun's activity. When a solar storm reaches Earth, one of its most direct effects on humans is through radiation. High-energy particles from the sun can penetrate the upper atmosphere and reach altitudes where commercial aircraft and astronauts operate. At ground level, the atmosphere provides a thick shield, absorbing most of these particles, so radiation levels remain low and largely harmless. However, at cruising altitudes of 9 to 12 kilometers, especially on polar routes where Earth's magnetic field is less protective, the exposure is higher. Passengers and crew are subject to increased cosmic radiation during these flights. The effect is gradual and cumulative. Occasional travelers receive minimal additional exposure, while frequent flyers and flight crews accumulate slightly higher doses over time. Astronauts in space face more direct exposure. The magnetosphere offers limited protection in low Earth orbit, and beyond it, in deep space or lunar missions, radiation levels increase significantly. Space agencies carefully calculate allowable doses based on scientific data to ensure safety. Spacecraft are equipped with shielding to reduce exposure, and mission duration is limited to prevent dangerous accumulation of radiation in the body. The primary concern is high-energy particles from solar storms, which can penetrate skin and equipment, potentially affecting cells and DNA. Astronauts are trained to monitor radiation levels and take protective measures, such as moving to shielded areas within the spacecraft during periods of strong solar activity. Radiation exposure can be measured scientifically using dosimeters and instruments that track particle flux. During moderate solar storms, the increase in radiation is noticeable, but still below levels that cause acute harm. In extreme cases, such as an intense CME, astronauts may be advised to remain in protected areas for the duration of the storm. The effects on humans are physical, following the interaction of energetic particles with tissue and cells. Short-term exposure at typical flight altitudes produces no immediate symptoms, but prolonged or intense exposure without protection can increase long-term health risks. This includes small elevations in cancer risk or potential changes to cell structure over time. For commercial passengers, the main difference during solar storms is a slight increase in background radiation. This is measurable, but not dramatic. High-latitude flights, especially over polar regions, are more affected because Earth's magnetic field lines guide charged particles toward the poles. Airlines track space weather and adjust flight paths if needed, moving planes to lower latitudes where the field offers more protection. Pilots receive information about increased radiation and potential communication disruptions caused by geomagnetic storms. The physical process is continuous and predictable. Charged particles collide with atmospheric atoms, producing secondary radiation, which then interacts with the aircraft and human bodies inside. Indirect effects of geomagnetic storms on health are more subtle. Some studies suggest small changes in the Earth's magnetic environment may influence circadian rhythms or sleep patterns, but these effects are minor and scientifically uncertain. Unlike radiation, which is measurable and quantifiable, other potential health effects are still under investigation. There is no evidence that geomagnetic storms produce direct psychological or physiological harm to the general population. The main concern remains exposure to energetic particles at high altitude or in space. Understanding the distinction between measurable effects and myths helps maintain clarity and avoids unnecessary alarm during solar storms. Astronauts rely on detailed models of solar activity to plan missions and mitigate risk. Satellites measure incoming particle flux, energy levels, and magnetic orientation, providing real-time data. Predictive models estimate radiation exposure for crew members, allowing protective measures to be taken. Shielded sleeping quarters or control areas can reduce exposure during periods of intense solar activity. Even in the harsh environment of space, careful planning and understanding of particle behavior enable humans to work safely, illustrating the predictable nature of physical processes during solar storms. Geomagnetic storms can influence technological systems that indirectly affect health. For example, power outages caused by induced currents in transformers may disrupt heating, refrigeration, or medical equipment. Communication disruptions can interfere with emergency response. These are not direct effects of the storm on the human body, but they represent secondary consequences of the interaction between charged particles, magnetic fields, and human infrastructure. Careful planning and resilient systems can mitigate these indirect risks, ensuring that people remain safe and secure during solar activity. Scientific measurements of radiation during flights show small, incremental increases during solar storms. The magnitude depends on altitude, latitude, and storm intensity. Instruments such as Geiger counters, dosimeters, and particle detectors provide precise readings, allowing airlines and space agencies to respond appropriately. The physical process is straightforward. Energetic particles enter the atmosphere, collide with atoms, produce secondary radiation, and interact with human bodies. Protective measures such as flight adjustments or shielding reduce exposure and ensure safety. The calm, predictable flow of these processes reflects the natural and measurable influence of the sun on human activity. For those on Earth's surface, geomagnetic storms do not increase radiation in a way that poses immediate health risks. The thick atmosphere absorbs nearly all incoming high-energy particles before they reach ground level. Some minor increases in cosmic rays occur, but these are indistinguishable from natural background radiation over short timescales. Scientific monitoring confirms that ordinary people are largely unaffected by the radiation component of solar storms. Most observable effects are limited to technology and the upper atmosphere, rather than the direct human body at sea level. In space, astronauts' exposure is cumulative and carefully managed. Long-term missions, such as stays on the International Space Station, involve constant monitoring of radiation levels and careful scheduling of activities during solar storms. Space agencies maintain databases of radiation dose, track historical solar activity, and plan missions to avoid periods of intense solar storms when possible. Protective shielding in spacecraft, combined with operational protocols, allows humans to function safely in an environment with radiation levels far higher than at Earth's surface. The principles governing this exposure are based on the interaction of charged particles with matter and magnetic fields, measurable and predictable. Radiation is not the only consideration. Solar storms can affect the reliability of systems that support human life. Communication satellites may experience temporary failures, GPS signals may fluctuate, and electrical grids may undergo fluctuations. While these effects are indirect, they can influence safety in aviation, navigation, and emergency response. For example, a disruption in GPS could lead to temporary rerouting of flights or shipping vessels. The effects are physical, resulting from interactions between energetic particles, the magnetosphere, and technological systems that support modern life. Understanding these links allows risk to be managed calmly and systematically. Calm, factual observation of geomagnetic effects distinguishes reality from myths. Popular stories sometimes exaggerate the immediate danger of solar storms to human health. In truth, measurable effects are limited to high altitudes and space. Astronauts and flight crews receive higher doses, but these are carefully monitored and managed. Ordinary people on the ground experience negligible radiation increase. The science is clear. Solar storms are energetic and influential on technology, but direct health impacts on the general population are minimal. Clear communication of these facts helps maintain perspective and avoids unnecessary concern. Physical principles explain the effects succinctly. Charged particles from the sun follow magnetic field lines into the atmosphere. There, they interact with atoms, producing light, currents, and radiation. The energy transfer is predictable and measurable. Biological tissue absorbs some of this energy at high altitudes, while the surface remains largely unaffected. Protective measures, such as flight rerouting and shielding in spacecraft, are based on the same physical principles. The response of humans to radiation is understood through decades of research, allowing safe operation of aviation and space systems even during significant solar activity. Radiation exposure during solar storms is gradual, continuous, and distributed over time. Acute effects are extremely rare and occur only in situations with prolonged exposure to high-energy particles without shielding. In normal aviation or space operations, exposures remain within limits established by scientific research. Instruments track particle flux and dose, providing real-time information for mitigation. The underlying physics is straightforward. Energy transfer occurs through particle collisions, interactions with magnetic fields, and absorption by matter. These predictable processes allow humans to operate safely despite the dynamic environment. Monitoring of space weather continues to improve safety for humans. Satellites detect CMEs, measure particle energy, and transmit data to Earth. Alerts are issued to aviation, space agencies, and other affected sectors. Radiation forecasts guide flight paths, shield astronauts, and prevent excessive exposure. Scientific understanding ensures that human health is protected while still allowing normal operations. The calm, deliberate management of these effects reflects the measured, predictable interaction between solar storms and living beings. Even during major solar storms, measurable effects on human health remain confined to specific contexts: astronauts in space and passengers on high-latitude flights. These groups are aware of exposure and take protective measures. The general population experiences indirect effects only if technology or infrastructure is affected, which are managed through planning and redundancy. The observable consequences are consistent with the physics of charged particles, magnetic fields, and energy transfer. These processes are silent, continuous, and quantifiable, rather than sudden or dramatic, making them suitable for calm observation. Human health and safety during solar storms is a matter of measurement, monitoring, and mitigation. Direct radiation exposure is highest for astronauts and high-altitude flights near the poles. The atmosphere and magnetic field protect the surface population. Indirect effects through technological disruptions are managed through infrastructure design and operational planning. The distinction between measurable scientific effects and myths is clear, allowing a calm understanding of how solar storms influence human life. Observing these interactions provides insight into the natural, continuous processes connecting the Sun, Earth, and human activity without exaggeration or speculation. Human records of solar storms extend back over centuries, providing insight into how these events have interacted with Earth's environment and technology. The most famous recorded solar storm is the Carrington event of 1859. Observed by British astronomer Richard Carrington, it began as a series of solar flares, followed by a massive coronal mass ejection that struck Earth within 17 hours. Telegraph systems, which were the most advanced communication technology at the time, experienced widespread malfunctions. Operators reported sparks jumping from equipment, some wires catching fire, and the ability to send messages even when telegraph power was disconnected due to induced currents in the long lines. Auroras, normally confined to polar regions, were observed as far south as the Caribbean and Hawaii, illuminating the night sky in bright reds and greens. These observations provide a vivid record of how solar energy can transfer across millions of kilometers from the Sun to Earth. The Carrington event remains the benchmark for extreme solar storms. Researchers analyze the data to understand the physical processes and to model potential effects on modern infrastructure. Historical accounts describe auroral displays over large areas, demonstrating that the magnetosphere and atmosphere respond visibly to intense solar activity. The event illustrates that solar storms can deliver energy sufficient to influence both natural phenomena and human-made systems. Scientific examination of these observations allows us to correlate the strength of solar flares and CMEs with the scale of terrestrial effects, providing guidance for contemporary risk assessment. Other notable solar storms in the 20th and 21st centuries provide further insight. In 1921, a strong geomagnetic storm affected telegraph lines and early electrical networks. Operators reported induced currents that disrupted communication and caused local fires. During the March 1989 geomagnetic storm, the Hydro-Quebec power grid collapsed due to transformer saturation from geomagnetically induced currents. Millions of people experienced power outages lasting hours. Aurora displays extended to mid-latitudes, providing additional confirmation of widespread geomagnetic effects. The Halloween solar storms of 2003 caused satellite anomalies, airline rerouting, and minor electrical disturbances. These events, though less extreme than the Carrington event, demonstrate that solar storms continue to influence technology and provide measurable data for scientific analysis. Auroral observations in historical records are particularly valuable. In many cases, unusual sightings at low latitudes indicate periods of intense solar activity. Accounts from sailors, explorers, and astronomers document the colors, shapes, and movements of auroras during strong geomagnetic storms. These qualitative observations complement quantitative data, helping reconstruct past solar events. By examining the latitudes and duration of auroral visibility, scientists can estimate the energy of the corresponding solar storm and the intensity of geomagnetically induced currents on Earth. This information contributes to models of historical space weather and its potential impact on society. Beyond written records, natural archives provide evidence of solar storms over longer timescales. Ice cores from Greenland and Antarctica contain elevated levels of beryllium-10 and other cosmogenic isotopes, which are produced when energetic particles collide with atoms in the atmosphere. Tree rings capture carbon-14 variations, reflecting changes in cosmic radiation reaching the surface. These proxies allow scientists to identify periods of heightened solar activity, even when human observations are absent. By analyzing isotope concentrations over centuries or millennia, researchers can estimate the frequency and magnitude of extreme solar events and compare them with historical records like the Carrington event. Satellite records, beginning in the mid-20th century, offer direct measurements of solar particle flux, magnetic field orientation, and geomagnetic activity. Instruments in space continuously monitor solar flares, coronal mass ejections, and solar wind conditions. Data from these satellites have allowed the creation of statistical models that estimate the likelihood of solar storms of varying intensity. These models indicate that extreme events like the Carrington event are rare but possible. Observations of less intense storms provide a continuous record, showing patterns of solar activity over decades. Combining satellite data with historical records enhances our understanding of solar storm frequency, magnitude, and potential impact. The combination of historical accounts, natural proxies, and satellite measurements allows scientists to analyze patterns in solar activity. Solar storms are influenced by the Sun's 11-year cycle, during which periods of increased sunspots and magnetic activity correlate with higher frequencies of flares and CMEs. Extreme events do not occur with regularity, but show some clustering around solar maxima. Statistical analysis estimates the probability of extreme events over decades or centuries, providing context for planning and preparedness. These probabilities inform risk assessments for power grids, satellites, aviation, and other sectors sensitive to space weather. Comparing events across centuries highlights changes in human vulnerability. The Carrington event caused minimal disruption to society because the technology of the time was limited to telegraph networks. In contrast, the 1989 Quebec blackout demonstrated how modern electrical grids are susceptible to geomagnetic effects. Satellite-based navigation, global communications, and extensive power distribution networks now extend human exposure to solar storm consequences. Historical patterns help predict potential scenarios in contemporary contexts, providing guidance for mitigation and response strategies. Understanding past storms is crucial for anticipating future challenges. Scientific analysis of geomagnetic intensity during historical storms relies on magnetometer records where available, as well as inferred data from auroral observations. Measurements of the Earth's magnetic field provide information about the duration, strength, and structure of geomagnetic storms. These measurements, combined with knowledge of solar wind speed, density, and magnetic orientation, allow scientists to reconstruct the physical processes driving the observed effects. This reconstruction provides a clear link between solar activity, particle flux, magnetospheric response, and terrestrial phenomena, enabling predictive models for future storms. Observations of telegraph and electrical systems during historical storms reveal the mechanisms by which geomagnetic energy propagates through human technology. Induced currents in long conductors, transformer saturation, and local equipment damage were all recorded and analyzed. These empirical data provide case studies for engineers and scientists studying geomagnetically induced currents. Understanding how energy flows from the sun through the magnetosphere and into infrastructure informs the design of modern systems capable of withstanding solar storm effects. The continuity between historical and modern observations reinforces the predictive power of space weather science. Aurora observations at unusual latitudes serve as a proxy for geomagnetic storm intensity. During extreme events, the auroral oval expands, bringing the glowing lights to regions far from the poles. Reports of auroras over the United States, Europe, and the Caribbean during the Carrington event, for example, provide evidence of unusually strong particle flux and magnetic disturbance. Historical maps of auroral sightings help calibrate models of solar storm energy transfer. Observing the expansion and movement of auroras offers insights into the magnetosphere's behavior under extreme solar forcing. Ice core and tree ring records complement these observations. Sudden spikes in beryllium-10 or carbon-14 concentrations indicate periods of heightened particle radiation. These events can be correlated with documented auroras or telegraph anomalies to validate the proxy data. Analysis of these proxies over centuries allows reconstruction of the frequency of extreme solar storms, revealing that while they are rare, they are recurring phenomena. This long-term perspective helps scientists assess the probability of future events that could impact modern technology and society. Data from modern satellites also confirm patterns observed in historical records. Monitoring instruments detect solar wind velocity, magnetic field orientation, and particle density in real time. When extreme CMEs are detected, scientists can correlate these measurements with geomagnetic disturbances on Earth, including auroras, induced currents, and satellite anomalies. These observations reinforce patterns inferred from historical records and natural proxies, providing a continuous dataset that spans centuries when combined with older sources. By analyzing all sources of information, scientists can estimate probabilities for major solar storms. Extreme events similar to the Carrington event are rare, occurring perhaps once every several centuries. But moderate storms happen more frequently, often during solar maxima. These probabilities guide planning for technological infrastructure, satellite operations, aviation, and energy systems. The combination of empirical data, natural proxies, and satellite measurements allows informed decision-making, reducing vulnerability to solar storms while maintaining awareness of their natural and predictable physical mechanisms. Patterns also reveal variability in geographic impact. Magnetic latitude, ground conductivity, and infrastructure layout influence how geomagnetically induced currents manifest in different regions. Historical records, when combined with geophysical models, show that certain areas are more prone to electrical disturbances during solar storms. Understanding these spatial patterns allows utilities and government agencies to allocate resources and implement protective measures in regions at higher risk. The physical principles behind these variations are well understood, rooted in the interaction of magnetic fields, conductive materials, and particle flux. The study of historical solar storms demonstrates continuity in natural processes. Despite technological changes, the underlying physics of solar activity, particle motion, and geomagnetic response remains constant. Telecommunication disruptions in the 19th century and power grid failures in the 20th century both reflect the same fundamental interactions. By examining these events carefully, scientists can draw lessons about energy transfer from the Sun to Earth and the ways in which human systems can be affected. The historical perspective provides context for evaluating modern vulnerability and designing resilient infrastructure. Historical records also highlight the importance of continuous observation. Without systematic data collection, the precise timing, magnitude, and effects of past storms could be underestimated. Observations of auroras, equipment, anomalies, and magnetic fluctuations have allowed reconstruction of past solar activity. Coupled with modern measurements, these records form a long-term dataset that informs predictive models. Understanding the frequency, intensity, and consequences of historical solar storms supports the development of strategies to protect technology, infrastructure, and human safety from future events. Predicting solar storms has become a central focus of space science because the effects on Earth and human technology can be significant. Scientists rely on an array of satellites that continuously monitor the Sun and its surrounding environment. The Solar and Heliospheric Observatory, known as SOHO, provides imagery of the Sun's surface, capturing sunspots, flares, and coronal mass ejections in real time. STEREO, or Solar Terrestrial Relations Observatory, uses two spacecraft positioned at different points in space to create a three-dimensional view of solar activity. The Parker Solar Probe travels closer to the Sun than any previous mission, directly measuring the solar wind, magnetic fields, and particle flux. Together, these instruments provide a continuous flow of data, allowing scientists to observe the processes that may lead to geomagnetic storms long before their effects reach Earth. The detection of solar flares or coronal mass ejections begins the early warning process. Satellites measure the speed, density, and magnetic orientation of ejected solar material. Scientists analyze these measurements to estimate when the material will arrive at Earth, the likely intensity of the storm, and which regions of the planet may be most affected. This prediction process is grounded in the physics of particle motion and electromagnetic interaction. Charged particles follow predictable paths along their interplanetary magnetic field, and the interaction with Earth's magnetosphere can be modeled using well-established equations. These forecasts allow preparation time, which may range from several hours to a few days, depending on the speed of the solar storm. Early warning systems are linked to various industries and agencies that manage technology sensitive to space weather. Power grid operators receive alerts that allow them to adjust loads, activate protective devices, or temporarily shut down vulnerable transformers. Satellite operators can switch satellites to safe modes, reorient solar panels, or delay sensitive operations. Aviation agencies receive notifications to consider rerouting high-latitude flights to reduce radiation exposure and maintain reliable communication. These responses are all guided by real-time observations and predictive modeling, ensuring that human systems remain resilient in the face of solar activity. Mitigation strategies for power grids are particularly well studied. Geomagnetically induced currents can flow through transmission lines, saturating transformers and producing heat that may lead to damage. Utilities monitor geomagnetic activity and can redistribute loads, adjust voltage levels, or disconnect certain lines to prevent cascading failures. In some regions, transformers are designed with additional tolerance to quasi-direct currents produced during geomagnetic storms. Protective devices, such as series capacitors and neutral ground resistors, reduce the flow of harmful currents. The physical principles behind these strategies are grounded in electromagnetic theory and the measured response of equipment to induced currents. Satellites employ a variety of mitigation strategies to withstand solar storms. Shielding materials, redundancy in systems, and operational protocols protect sensitive electronics from high-energy particles. Satellites may enter safe modes during predicted storms, limiting power draw and communications to reduce the risk of damage. Operators track space weather forecasts and adjust mission schedules, such as delaying imaging or data collection during intense particle flux. These precautions allow spacecraft to continue operating safely, despite the energetic environment of space created by solar activity. Aviation relies on both radiation monitoring and communications reliability. Alerts from space weather agencies inform airlines about regions with elevated particle flux, particularly near the poles where geomagnetic protection is weaker. Flight routes may be adjusted to lower latitudes, or altitudes may be slightly reduced to increase shielding by the denser atmosphere. Air traffic control and onboard communication systems are prepared to use backup channels if high-frequency radio is disrupted. Crew members receive information about cumulative radiation exposure to ensure safety. These measures exemplify how predictive information translates directly into operational decisions for human safety. Scientific collaborations play a central role in predicting and preparing for solar storms. Agencies such as NASA, the European Space Agency, the National Oceanic and Atmospheric Administration, and research institutions worldwide share data, coordinate satellite observations, and develop models of solar activity. International communication ensures that warnings are distributed promptly to regions that may be affected. Researchers refine predictive algorithms by comparing satellite data, historical records, and computer simulations, improving the accuracy of forecasts. The collaborative approach strengthens the global capacity to respond effectively to geomagnetic events. Government agencies are responsible for translating scientific predictions into practical guidance. National space weather centers issue alerts and recommendations for critical infrastructure, including electrical grids, aviation, satellite operations, and emergency services. Policy frameworks support preparedness planning, ensuring that protective measures can be implemented quickly. Governments also fund research into improved monitoring technologies, materials, resistant to geomagnetic effects, and operational procedures for vulnerable sectors. This multi-layered approach integrates science, engineering, and public safety to mitigate the impact of solar storms on society. Prediction of solar storms involves modeling the Sun-Earth system as a whole. Scientists simulate the launch of a coronal mass ejection, its propagation through interplanetary space, and its interaction with Earth's magnetic field. These models consider the density, velocity, and orientation of solar particles, as well as the shape and strength of the magnetosphere. By inputting real-time observations from satellites, models can provide updated forecasts that estimate storm arrival time and intensity. These predictive capabilities allow human systems to respond proactively rather than reactively, minimizing potential disruption and damage. Historical experience informs preparation strategies. Lessons from events such as the Carrington event and the Quebec blackout illustrate the vulnerabilities of technology and infrastructure. Models now incorporate these historical data points to improve reliability of forecasts and determine which systems are most at risk. Utilities, satellite operators, and aviation agencies use these insights to design protective measures and operational protocols. Understanding the historical record allows mitigation strategies to be tailored for both moderate and extreme solar storms, ensuring that human technology is resilient across a range of conditions. Predictive strategies extend beyond technology to societal planning. In the event of an extreme solar storm, contingency plans may involve temporary modifications to transportation schedules, rerouting of communications, or prioritization of critical power delivery. Emergency management agencies use forecasts to prepare hospitals, communication centers, and essential services for possible disruptions. Coordination between scientific agencies, operators, and government bodies ensures a measured, effective response. This demonstrates that predicting solar storms is not merely a scientific exercise, but a practical tool for safeguarding modern life. The combination of real-time monitoring, predictive modeling, and mitigation strategies forms a layered defense. Satellites observe solar activity, models predict impacts on Earth, and operators implement protective measures. Redundancy and resilience in technology, including grids, spacecraft, and aviation systems, reduce vulnerability. These layers rely on the physical laws governing charged particles, magnetic fields, and energy propagation. Understanding the predictable interactions between solar storms and human systems allows for timely, effective preparation, minimizing potential harm while maintaining continuity of operations. Scientific understanding of solar storms is improving continually. Missions such as the Parker Solar Probe provide unprecedented data on the Sun's atmosphere and particle acceleration. Observations of coronal mass ejections, solar flares, and solar wind variability, refine models of storm onset and intensity. Space weather forecasting integrates these measurements to provide increasingly accurate and timely warnings. By combining satellite observation, historical analysis, and computational modeling, the scientific community enhances its ability to predict and prepare for solar storms with confidence and precision. In practice, early warning allows each sector to implement targeted measures. Electrical grids can redistribute load, activate protective devices, or temporarily disconnect vulnerable transformers. Satellites can be switched to safe modes, communication systems can use backup pathways, and aviation operations can be adjusted. Governments coordinate emergency management and public communication to reduce societal risk. Each step relies on accurate prediction and understanding of the underlying physics. The chain of preparation follows directly from the interaction between solar activity, Earth's magnetic field, and human infrastructure. International collaboration extends the reach of predictive capacity. Sharing of satellite data, research findings, and operational experiences ensures that all regions of the world can respond appropriately. Space weather centers operate continuously, monitoring the sun and providing alerts in real time. Researchers refine models by analyzing recent events and historical patterns. This networked approach enhances preparedness, ensuring that both scientific and operational communities can mitigate the effects of solar storms on technology, transportation, and human safety. Predictive and preparatory measures illustrate the interplay between natural phenomena and human planning. The sun generates charged particles and magnetic disturbances. Earth's magnetosphere and atmosphere interact with these particles. Human infrastructure is sensitive to currents, radiation, and communication disruption. By observing, modeling, and mitigating, humans can reduce the impact of these natural forces. This cycle of prediction, preparation, and protection exemplifies a careful, scientific approach to living within the dynamic space environment created by the sun. Looking ahead, scientists study the sun and its cycles to understand what might happen in the coming decades. The sun follows a roughly 11-year cycle, moving from periods of low activity, called solar minimum, to periods of high activity, called solar maximum. During solar maximum, sunspots appear more frequently, solar flares occur more often, and coronal mass ejections are more likely. Observations over centuries show that solar activity varies naturally, sometimes producing clusters of intense storms. Understanding these cycles allows researchers to project possible periods of increased space weather and to estimate the likelihood of extreme events. One area of focus is the probability of another Carrington-level event. Using historical records, natural proxies such as ice cores and tree rings, and satellite data, scientists model the frequency of extreme solar storms. Estimates suggest that events of similar magnitude to the Carrington event occur roughly once every 500 to 1,000 years, though the timing is uncertain. Moderate storms are more frequent and can still impact technology, but extreme events are rare. Despite their rarity, the potential consequences of a very large storm make careful monitoring, preparedness, and risk assessment important for modern societies. Predictive models rely on combining physics-based simulations with empirical data. Scientists simulate solar flare energy, particle acceleration, and coronal mass ejection propagation. They then model interactions with Earth's magnetosphere, ionosphere, and technological systems. These simulations help estimate how much energy may reach the surface, which regions might experience the strongest geomagnetic currents, and which systems are most vulnerable. This data informs the design of power grids, satellites, aviation protocols, and emergency management planning. Understanding the physics allows for informed decision-making and the development of protective measures. Societal resilience depends on recognizing vulnerabilities and planning for contingencies. Electrical grids can be designed to handle induced currents, using robust transformers, protective devices, and operational protocols that limit damage. Satellite operators maintain redundancy, shielding, and backup systems to ensure continuity. Aviation agencies plan alternate flight paths and monitor radiation exposure for crew and passengers. Communication networks include fail-safes and alternative pathways to maintain functionality. These strategies, informed by scientific observation and modeling, reduce the potential impact of extreme solar storms on daily life. Technological resilience is a critical aspect of preparation. Power systems can be segmented to limit the spread of induced currents. Satellites can be hardened against energetic particles, and orbital adjustments can protect against increased atmospheric drag. Aviation protocols ensure safe navigation during periods of elevated radiation and ionospheric disturbance. Even pipelines and undersea cables, which can carry geomagnetically induced currents, are monitored and protected through grounding and voltage management. By integrating knowledge of the sun's behavior into system design, humans can coexist safely with natural energetic events. Environmental resilience is another consideration. While solar storms do not directly alter climate, they influence the upper atmosphere, temporarily heating it and expanding its layers. This expansion increases drag on low-orbit satellites and affects the density of atmospheric gases. Solar storms also ionize the upper atmosphere, affecting radio signal propagation and creating auroras. Observing these natural phenomena allows humans to anticipate temporary environmental changes without alarm. The rhythms of the sun, magnetosphere, and atmosphere are continuous and measurable, offering predictability within the vast system of space weather. Risk assessment integrates probability, vulnerability, and potential impact. Scientists weigh the frequency of extreme events against the sensitivity of infrastructure, technological systems, and human activities. By modeling scenarios, they identify critical points of weakness and design strategies to mitigate cascading effects. This proactive approach allows societies to maintain stability even when nature produces rare but powerful energetic events. Risk assessment is a calm, analytical process, grounded in observation and physics rather than speculation or fear. Monitoring continues to improve with advancing technology. Satellites such as the Parker Solar Probe, SOHO, and STEREO provide detailed measurements of solar activity, particle energy, and magnetic field orientation. Ground-based observatories track sunspots, solar flares, and geomagnetic variations. Combined, these observations form a real-time picture of space weather, allowing scientists to detect early warning signs of potentially disruptive storms. The integration of observational data with predictive models enhances confidence in forecasting and enables timely protective actions across technological and societal systems. International collaboration is central to forward-looking preparedness. Space weather agencies, research institutions, and operational centers share data, models, and alerts globally. Early warning networks ensure that information reaches power companies, aviation authorities, satellite operators, and emergency services. Lessons learned from historical events guide contemporary policies and infrastructure improvements. By working together, the global scientific and operational community can anticipate solar storms and mitigate their potential effects, reducing risk without disrupting normal life. The Sun's activity reminds humanity of the dynamic nature of the solar system. While extreme events can influence technology and human systems, they are part of a natural rhythm that has existed for billions of years. Observing these rhythms fosters an appreciation for the Sun's power, the protective role of Earth's magnetosphere, and the resilience built into technological and societal systems. By understanding these patterns, humans can coexist with space weather, maintaining safety and continuity even during intense solar storms. Preparing for the future involves both technological innovation and careful planning. Electrical grids can incorporate advanced sensors, satellites can include improved shielding, and aviation protocols can remain flexible. Emergency management plans account for temporary communication disruptions, power fluctuations, and other potential indirect effects. These measures, informed by historical data and modern science, provide confidence that society can endure rare extreme events without panic, relying instead on knowledge and preparedness. Scientific projections indicate that while extreme solar storms are possible, their occurrence is not predictable with certainty. Probabilistic models guide preparation by estimating likely magnitudes and impacts. Moderate storms, which are more common, serve as continuous test cases for infrastructure, technology, and operational readiness. Each storm observed in real time improves models, validates protective measures, and enhances human understanding of the Sun-Earth connection. These incremental improvements build resilience gradually, reducing the likelihood of catastrophic disruption. Reflecting on the future, it is clear that solar storms will continue to influence life on Earth in subtle and measurable ways. Auroras will paint the skies, geomagnetic currents will flow through power systems, satellites will experience particle flux, and high-altitude travelers will encounter small increases in radiation. These interactions are predictable and manageable with knowledge, preparation, and observation. The Sun's activity, while powerful, is part of a system that humans can study and understand, creating an opportunity to live in harmony with natural cosmic rhythms. The calm observation of space weather encourages a sense of continuity. Each solar cycle follows its patterns. Each geomagnetic storm transfers energy according to predictable physics, and human systems adapt through engineering and planning. By studying these processes scientifically, humans gain confidence in their ability to maintain technological, societal, and environmental stability. The Sun's rhythms, once mysterious and alarming, become measurable and integrated into daily life, illustrating that natural forces, even when extreme, are not beyond human understanding or management. Looking forward, the perspective of space weather combines caution with reassurance. Knowledge of potential risks informs preparation, while observation of natural patterns reinforces predictability. Infrastructure, technology, and human operations continue to evolve in response to understanding, making resilience increasingly robust. Each new observation, each improved model, and each operational adjustment contributes to a framework in which society can coexist safely with solar activity, minimizing disruption and fostering calm confidence in the natural order. In conclusion, scientific projections for the coming decades emphasize both the possibility of extreme solar storms and the capacity for preparation. Risk assessment, predictive modeling, and technological resilience allow societies to maintain continuity. Observing the sun, monitoring geomagnetic activity, and planning for contingencies integrate knowledge into action. The rhythms of the sun, the flow of particles, and the responses of Earth's systems form a continuous, understandable cycle. By respecting these natural forces and applying scientific understanding, humans can live safely and calmly within the dynamic environment of space, appreciating the quiet, powerful rhythms of the cosmos without fear.